Computer Science 330 Lecture number 4, August 27, 2020. Okay, today we'll be we're also going to have a short video. It'll be about SPI, serial communication. So last time we learned about UART. Okay, today we'll be talking about SPI, and there'll be a couple of videos I will want you to watch. That's the robot we'll be working with. Homework will be due on Monday. Please take notes while you watch this video and submit them by midnight, as usual. Okay. First off, one of the things I want to talk about, also like theory-based, I guess, chip select and negation, signal negation. Okay, so the way UART works is that kind of you have two computers and they kind of talk to each other, right? Unfortunately, as far as I know, you can't really have one computer which will be talking to like one device which will be talking to a huge amount of other devices, right? So you can't really hold on. You can't really have, again, like one device which will be talking to this guy, this guy, this guy, and this guy at the same time, right? Because you have RxTX, and each one of them has RxTX, right? So it doesn't really work that way. Yeah, that's why the stuff which we'll be talking about today, which is SPI, another way of communication between the two devices, another protocol, it has so-called chip select. Okay, so-called chip select. So what does it do? It basically allows you to have one device talking to multiple devices. Okay. So you have one device, and you kind of allowing that device to control, let's say 4, 3, 2, 1. In the simplest case is 1, of course, but I don't know, 5 multiple devices. Okay. But again, but the wires, not like you're gonna have, for example, if in order to establish connection to one device, you need to have 4 wires. And now, if you have 4 devices, if you want to talk to 4 devices, not like you need to have 16 wires, because that kind of doesn't make any sense. In that case, it's just easier to create 4 UART ports, right? What happens is that those RxTX, or that like analog of that counterpart is still is the same for all of the 4 devices on the right. However, what's going to be changed though is we're going to add a few additional wires which are going to be called chip select. Okay. So basically, again, these wires are not going to be changed at all, right? They'll be just kind of splitted and going into all of the devices on the right. However, what's going to happen though is we're going to create one more. We'll introduce one more wire, and that wire will be dedicated you'll be dedicated to each one of the computers on the right. Okay, so basically that's 1, that's 2, that's 3, and that's 4. Okay. Yeah, perfect. So that wire is called chip select, which basically means that one of these wires is going to be set to active by this guy over here, right? For example, if this guy wants to talk to this guy, in that case, this wire is going to be transmitting like the active signal, right? And all other 3 wires will be transmitting not active signal. Okay. And in this case, this guy over here is going to understand, okay, so whatever is being transmitted, it's being transmitted to me, not to anyone else. Okay. And this guy over here, for example, well, let's change it. Okay. And this guy over here, see, he's also going to be receiving the same message, but since the chip select wire is going to be not active, he's going to understand, okay, so I'm receiving some message, but since chip select is not active, this message is not meant to me, so I'm going to completely ignore this. I'm going to disregard that. Same thing over here, same thing over here. Usually, again, to the best of my knowledge, you can directly talk to only one device. You can't really send the message to both of them. Well, why not though? I don't know. But normally, you talk to only one of them. Okay. Yeah, so that wire is called chip select signal, okay? And usually it's spelled this way, so you're gonna have like C, and then you're gonna have S, and then you're gonna have a horizontal bar on top of it. So what does that horizontal bar mean? that means negation. What does that mean? That means normally, if let's say chip select was without that horizontal bar, okay, without that, okay, if there was just chip select, that means that whenever this wire is set to like positive 5 volts, as I was talking about last time, but basically digital it will be 1, right? If it is set to 1, right, then most likely all the rest are set to 0, right? And then active level is being set to 1, which means that if the wire is pulled to 1 to 5 volts, that means that activates this device. Okay, that's what the normal operation looks like. However, when we add this vertical horizontal bar on top of it, that basically reverses the entire thing. That means the active level now becomes 0 and 1 being not active level. What does it lead to? It leads to the following. And that means if I want to talk to this guy, I need to pull this wire down to the ground, so it's going to be 0. Okay, here we're going to have 1, here we're going to have 1, here we're going to have 1. Okay, so 0 and 1. So that means out of all the devices, if I want to talk to that guy specifically, I will be pulling the chip select down, but by default it's going to be 1. Okay, so basically 1 means it's inactive, 0 means it's active. Okay, so that's what that vertical bar means. It was just historically formed that way, that in SPI chip select is negated, basically because it's very easy to have some noise on the line. It's very easy to go from, like, for some kind of, it's very easy to create 0, but it's very easy to create 0, and if there is some noise, it can jump from 0 to 1. But if you have 1 being not active, then all the people you're trying to talk to, they definitely know that it's impossible to have a mistake when something is set to 1. Okay, so it's definitely inactive. Not sure if it makes sense, but basically, again, because of how the wires work and how you can have electromagnetic field and how they can create some additional current, that's basically a lot more stable to work that way with negation of chip select. By the way, since you see kind of this guy is talking to all of them, not like this guy is talking to all the rest, right? But this particular computer, this particular device is kind of the main, right, among those 4. Like, he decides who to talk to, he decides who how to select, like so he's kind of like has the leading role, right? So he is the person or the computer who decides everything, and that's why, for that reason, that device is called master, right? Because he leads the conversation. It's all about up to him, and all of the other guys who he's connected to are called slaves. So slave 0, for example. No. Yeah, for example, slave 0, slave. No, can't do that. Okay. Yeah. Slave 1, slave 2, slave 3. And usually in that case, chip select will also be labeled the same way. So it's going to be chip select 3, chip select 2, chip select 1, chip select 0, with the horizontal bar on top of them, on top of each one of them. Okay. So those are the labels of the pins on the master. Okay. Hope it makes sense. Again, in UART, as far as I know, that's not possible, because it's all about like 2 parties and how they communicate to each other. So in our case, we're going to have the robot and we're going to have the computer. They communicate, they talk to each other. So we're going to use UART. Whenever we have multiple system, like multi-device system, right? Chip select and SPI, it's another protocol, right, which we'll be talking about today, is more beneficial. Okay, let's watch this video together. I'll be adding some comments. Just this guy explains it like super really well, and he has like an amazing voice, by the way. I hope you can hear this. Yeah, so I hope you'll be able to hear that. If not, just play it in a separate tab on your browser alongside with me at the same time. Okay. So it's what is SPI, and it's microchip technology. It's basically a company. So whenever a huge company like IBM, something like this, whenever you see a promo video from a company which is not specializes, which doesn't specialize in art and media, it's usually super boring and dull, and it's like very, very different. So in this case, the guy has like outstanding voice, in my opinion.
From the host series. So what's SPI? SPI is an acronym for Serial Peripheral Interface. Hardware.
Yeah, so serial peripheral interface. So peripheral interface, don't think about that, but serial, what does that mean? That means we're sending all the bits serially, so like it's like a one wire, and we send the signal in that one wire, right? So we send bits like one after another, not like in parallel, where we're gonna have 8 wires, and the data will be sent in parallel, right, in 8 wires.
Folks will refer to the interface as SPI. Software folks will tend to say SPI. SPI was created in the mid-1980s. To gain that throughput speed, an additional signal was needed.
Yeah, so SPI, I2C, I2C, is which is another protocol. So SPI, UART, I2C are kind of competitors, right?
Isolate data to and from the host. Because of this, about twice as many logic gates are needed to implement SPI over I2C, which means that SPI device, higher density SPI memory, and SRAM device, consumer electronics. But because SPI serial clock or SPI is
so where is it
industrial
used?
equipment, automotive, and aerospace. SPI is also referred to as a 4-wire bus, as there are 3 bus signals.
Okay, 4-wire bus, right? So there are 4 wires in communication, right? So that we have a master, we have a slave, and here we have 3, right? So which one are we missing?
Clock or SEK.
SEK,
Master out, slave in, or mobile.
Yeah, so we have also 2 additional, so we're missing chip select, of course, right? So there are 4 wires, 1 chip select, another one is serial clock, right? So remember like UART, USART, right? So in UART, we had a, USART synchronous, right? In UART, in UART we didn't have a clock, but here in SPI we do have a clock. So it's called SCK, serial clock. Now MOSI, right, and MISA. So MOSI stands for master out, slave input. What does it mean? That means it's a wire which transmits the data from master out, slave input. So it goes from master to the slave. And MISA means the opposite, master input, slave output, which means it transfers the data from slave into master. So master in, right, slave out.
MOSI and master in, slave out, or MISO. But because SPI does not include a slave addressing method in the protocol, a 4th signal, chip select or CS, is needed to select each slave. Here's an example of 4 devices connected to the same SPI bus.
Okay, so check this out. This dot, in electrical engineering, that means the wire is going to be split into 1, 2, 3, right? So for example, what do we have here? Chip select, a dedicated wire for chip select 0, right? Then chip select 1, chip select 2. So we have 3 slaves, and that's why we have 3 chip select wires. Okay, perfect. Now clock, we're gonna have 1 clock. So this clock is split between this guy, and this guy, right? So all of them receive exactly the same clock signal. Same thing for MOSI and MISA, right? So it's split here, and it's shared between the 3 slaves, and for MISA as well, it's shared between the 3 slaves. So the way it's going to operate is this. Master is going to send a command to one of these guys, right? So how's that going to work? It's going to send the clock, always it sends the clock, and then it's going to send some signal for this wire, MOSI, master input, master output, slave input, okay? Since it is shared, right, between 3 slaves, each one of those slaves is going to receive the signal, okay? This guy, and this guy. However, they're all going to disregard that data unless chip select is 0, okay? So for example, if this chip select is equal to 1, if this is equal to 1, if this is equal to 0, then this guy is going to disregard the message, this guy is going to ignore it, this guy is going to understand that he's talking to him, right? if let's say this guy that's set to, let's say 1, 1, and 1, then kind of, although you send in the data, each one of them is going to think that you're not talking to him, right? And that's each one of them is going to ignore it. If let's say you set all of them to 0, that which is very, very unlikely to happen, then each one of them is going to think that a master is talking to him. So it's going to they're all going to kind of receive the signal. They're going to try to decode it, try to understand what that signal means, and it's going to reply using the other wire, and that's going to become a problem. If they all try to reply at the same time using MISA, master input slave output, you'll be complete unpredictable behavior.
The microcontroller is the SPI bus master, and the 3 slaves are an A to D converter, a serial EEPROM, and an LCD. Note that each slave device needs its own CS signal, or I/O port, on the MCU. That is a total of 6 signals versus the 2 signals in a 3-slave I2C system. But remember, we gained throughput speed with SPI. SPI protocol defines 4 modes.
Okay, so we're not interested in the modes, it's not that important, but we need this though.
Top 3 signals, CS, SEK, and MOSI, are all generated by the SPI bus master.
Okay, so it's very important, like when you have, like when you're talking to somebody, or like when there are, I don't know, 2 computers talking to each other, it's very important to understand, so for each wire, who's kind of generating the signal and who's listening to the signal, right? So these 3 green signals, right, are generated by the master. They go from master to the slave, and this red wire is the signal there is generated by the slave, and the master is just listening to it.
And the bottom signal MISO is generated by the slave that is selected. To start an SPI transaction, the master must select the slave device by asserting CS or driving CS low. This tells the specific slave to listen for an SPI command, also called an opcode. After CS has been driven low, the master then generates clocks on SCK to shift command and or data bytes into the slave using the MOSI signal. The number of
so this can probably be seen confusing, right? So it's not like 0, it's not 1, not sure what that is. That basically means like you send in either 0 or 1. So that's kind of like a weird way of showing that you send in either 0 or 1. You just show like a snake like this. Basically, you can go either that way, like that way, to the bottom, or to up, like upper portion of it, or you can just like kind of change in between all the time. Okay, so basically what he's trying to say is that we're going to have 8 bytes from D0 to D7, sorry, bits, 8 bits, right? So 8 either zeros or ones. Okay, and how do we know kind of like how many of them and when to read? We have a clock. So basically the same system is going to happen as I told last time.
data bytes transmitted is dependent on the transaction type and the design of the slave device being accessed.
So that's basically data byte number 0. That's the first one which is going to be sent, and that's going to be received. And then you can send, I don't know, 100 bytes, 200 bytes, 1000 bytes, right? You send them the 0th one, the first one, the second one, the third one, and then up until some kind of n.
When the master requests data from the slave will transmit the requested data to the master on the MISO signal.
Okay, so for example, it happens in situations like this. Let's say we have a robot, right? And our computer is talking to the robot. And our computer is the master, the robot is the slave. And the computer is going to say like, hey, can you please give me the distance to the wall? Okay, and that's actually, that kind of sensor is embedded into our computer, into our robot. Yeah, so that's basically a request which is made from the master, from our computer, from our laptop to the robot. Okay, now robot is going to send a reply back which master needs to receive and decode and understand what it means. So, and that's approximately what's going to happen. It's going to send 1 byte of data, right, from master to the slave, and then after it received it, then there will be some time difference between kind of this moment of time and this moment of time. That's basically the time when robot is going to process information and understand what master wants from him, and then it's going to send a reply back.
Once the transaction is complete, the master terminates the SPI transaction by driving chip select high.
Right, yeah. So once chip select becomes 1, right, that means not active, the robot, the slave, is going to immediately understand, okay, so whatever I receive, it's not for me.
To deselect the slave device. Well, that is SPI. Now you understand.
Perfect. Okay, hope it makes sense. Very short introduction. I want you to watch... no, hold on. No. I want you to watch one more additional video which talks about, I would say, all 3 of those protocols. SPI, S230, and UART. Okay, I want you to take notes while you watch them. Then please submit the notes before the midnight, and I'll see you on Tuesday. Be ready for the homework on Monday. See you later. Bye bye.